Basta,
si vede qualcosa da lì.
Segnato che è registrato, così vero?
Vabbè, dai, si dovrebbe vedere.
Dove c'è che sta registrando?
L'ha detto. Recording in progress, non ci finiamo. Vedi, registrazione in corso. Non so poi come lo carichi in giro, quello lo faremo.
Ma rivela solo in per email, no?
Avrò visto appunto delle...
Ah, io devo... Metti... Solo Martina Monti c'è, Fede, boh.
Ne fatto lavagna in questo momento, se no se
Ci vuoi zoommiamo?
il computer. Se sono fate il computer verso di me, te lo ti muovo io.
Ci devo andare in link.
Io
Sì, sì, dovrebbe essere collegata. Ciao Marco.
Ciao, io vi sento e vi vedo.
Anche noi.
Beh, mi sa che allora possiamo iniziare.
No? Cioè, prova a vedere se gira. Ah, ok. Deve arrivare qualcun altro?
So.
Dubito.
Fede?
Fede non c'è oggi.
Ma... Boh?
Vabbè, dai.
Introduction?
Yeah.
Come on.
Seriously.
Today we are honored to have... Dove inizio il torno?
Sì, se riesci a fare su e giù le lavagne. Ah sì, certo.
Today is the first day of the seminar SemiVa. And our first speaker is Frabat for the friends. Francesco Battistoni. And
Italian Champions of Bang, let's see. Most important academic achievement.
And today he will give an introduction about elliptic curves.
Okay, thank you, Matteo. So today we start this tiny cycle of seminars about elliptic curves, and I wanted to start with a short introduction overview of why elliptic curves are important for several things in mathematics, like, for example, their role in geometry, their role in arithmetic, and if I have time, I would also like to say something about their role in cryptography, since they are really, really used right now in cryptography. I just said that Federico is not here because he was the one that organized everything, but I think he will be here for the next lessons. So, okay, let us start. And I think I want to start with just an introduction on the fact that this is, in some sense, a bad name for these objects. So, part 0 of the seminar will be just explaining briefly why these are not ellipses. Because people who don't know what elliptic curves are, maybe they can think that elliptic curves are ellipses in some sense. The answer is no. So whenever we have a thing like that, this is not an elliptic curve. Okay, this is just a reminder, but I want to explain why German people and French people in the 19th century used this definition that unfortunately we carry on today. Because the idea, in fact, for this name was the following. Assume that you have a circle and you want to compute the length of this arc of the circle. How can you compute this? You know from the basic courses in analysis that, okay, if this is the curve, which is defined gamma t equal to xt, yt, and the relation is this one, classical relation, then you know that you can compute the length of the arc of circle you're interested in by just integrating this. You have to take the integral of the square root of square of the derivative of x with respect to t, and square of the derivative of y with respect to t. And okay, now just do the computation. Compute here the derivatives. You substitute the terms in y with the terms in x using this relation. And then if you do the computation, you will arrive at this thing. Yes, which with a change of variables, just call z equal x of t, you will obtain this integral. Perfect. This is just change of variables. So the length of the arc of a circle, in fact, you just need to compute this integral. Now, from a basic analysis, you know what this integral is. It is the arc sine of z, which is, you know, the inverse function of a trigonometric function, the inverse function of sine of z. Okay, so this is the particular case whenever you're interested in the length of the arc of a circle. This length is given by the inverse of a trigonometric function, and in particular, you see here that the denominator, you can think of this as, let us call it u equal square root of 1 minus z squared, which again gives you exactly the equation of the unit circle. Now, suppose that you want to do the same thing, but instead of considering a circle, you consider a generic ellipsis. You can do exactly the same thing because, okay, you define your curve, the coordinates satisfy a relation like this with different coefficients, and you do the computations exactly like this. What is the problem now? The problem is that, again, you obtain an integral which in general would be of this form. Where you see now it is a bit more complicated because in general, instead of getting a quadratic, you obtain a cubic here where lambda is a real parameter.
So when you draw this arc, you mean the full thing, right?
Yeah, I'm taking for example, this arc of the ellipses.
Of the whole ellipse, you are just considering this part.
Yes, because yes, for symmetry, I just needed to consider on one part, especially because when I'm doing this integral, like here, I need to suppose that this is the graph of a function. So I just need to take a part. Okay, and when I do this, I arrive to this integral, which is now, in general, you cannot resolve this integral. You cannot resolve this by analytic formulas. But again, the idea is that there are two main ideas here. The first one is that exactly like here for the circle, the interesting object is not the integral, the arc sine, but its inverse function. So the idea is not to consider this integral, but to consider this the inverse of this. The inverse of this integral is called an elliptic function, which is called elliptic because you see it arises from this integral used for the computation of the arc of an ellipsis. This is the first idea, and here starts the theory of elliptic functions, which is widely studied. Elliptic functions satisfy some kind of periodicity, exactly like trigonometric functions with 2 parameters instead of 1. And there are many things that we can say. But the second idea is connected to this, because here we said, okay, from here, from the denominator of the integral, I recover again the unit circle. What is the curve that I recover instead? From here, I take u equal to all these square root. I go to the squares. This goes to u square equal to this cubic polynomial. And here you can see exactly an example of what we call an elliptic curve. And this is the reason why they are called elliptic curves, because are the curves that arises from this elliptic integral. And yes, it's not a good definition, in my opinion, because these curves are much more important than ellipses in some sense, and I will explain why in the next minutes. But unfortunately, since most of the modern mathematics is now done using definitions that arose in the 19th century, with all the good things, but also the bad things that this means, then now we are kind of forced to call these things elliptic curves. And we will call them elliptic curves from now on. Okay, this was the historical introduction of about the name of these things, but now I want to explain really what elliptic curves are, at least from a geometric point of view. So I'm going to give a naive definition of an elliptic curve. For us, an elliptic curve will be a curve given by the solutions of this equation. So in general, for me, an elliptic curve, at least from a naive point of view, will be take the points in the plane, which are the solutions of y squared equal to f of x, where f is a cubic polynomial. So you see this is exactly an instance of elliptic curve, because here you have u squared and here you have a cubic polynomial. So, for example, if I want to draw 2 instances of elliptic curves, probably some of these graphs you have already made them in the past, in the sense that they are typical examples of nice curves to draw in the plane. I can take, for example, y squared equal to x cubed minus 3x plus 3. And if I draw this in the real plane, it will be something like that, where I have the symmetry, obviously, between the up and down, given by y squared. If I draw instead y squared equal to x cubed minus x, I draw this in the real plane, and I have again a similar thing, but drawn like this. Probably you have already seen this kind of drawings in the past, if you ever read something about elliptic curves. But as I told you before, this is in some sense a naive definition, because there are some things that I have to mention about this. 3 things, actually. So, the first thing is that actually, when I talk about elliptic curves, I'm not really considering all the curves given by this equation, but I'm considering the non-singular ones. I want elliptic curves to be non-singular, which roughly speaking means that they have no singular points, so they have no singularities, no self-intersection points. And so, for example, if I take the curve given by the equation y squared equal to x cubed plus x squared, it is very easy to see that the graph does something like that. And here in 0, I have exactly a singular point. You can see also, if you do the classical procedure by looking at the derivatives in x and y, you can see that the derivatives are 0 exactly when x and y are 0. So for us, this is not an elliptic curve because this gives a singular point. Just like many curves in algebraic geometry, we want them to be non-singular. The second thing that I want to mention about the definition of elliptic curves is that, again, just like almost everything in algebraic geometry, actually, when I'm considering the curve, I need to consider the projective version of this curve. So I take, again, the curve that I drawn before, this one, x cubed minus x. Now I go to the projective version of this, and it becomes this cubic y squared z equal to x cubed minus x z squared. And why this is important? Because the thing now is that you can immediately see that in the projective plane, this curve always has a solution, which is this point. And I mean, it is in particular a solution which is not related to the affine version of the curve, because you see here that I'm taking z equals 0. So this is a point, an infinity point, in fact, that is not described by this equation. So elliptic curves are in fact curves for which I can always choose an infinity point. And in fact, I can give an equivalent definition of elliptic curves by saying that they are projective curves with a specified base point. And the fact that we have this infinite point, which usually people call this O, it will be very important for why elliptic curves are so important, especially from a geometric algebraic point of view. And now the last thing I want to say about the naive definition of elliptic curves is that, okay, here actually until now
So, like by the previous thing, did you mean to say, like, if you take the affine version,
Mhm.
it may or may not have solution?
Yeah, exactly.
So, but the projective always has a solution.
Yes.
So this you get by homogenizing and dehomogenizing.
Mhm.
So any polynomial like this, if I'm not wrong, there's a one-to-one correspondence between like these two things, right? You can always homogenize, and you can always dehomogenize.
Exactly.
So, but so the solution is not preserved under this transformation.
Okay.
Depende on which line you cut. Like, depends on how
I
you
mean,
cut them.
obviously, if I dehomogenize now with respect to y, I will see the solution now, because it will be the solution 0, 0 in this case.
But can you try to can you use this projective case to somehow get an idea of what a affine solution?
Uh,
No way.
I think it depends. The fact is that usually the fact is that elliptic curves, you can define them also in another way, but if they are elliptic curves, they will always reduce to a thing like that via transformation, change of variables, and stuff like that. So in the end, you will always end with a situation like this. I think the main difference, this will become now also a question of the genus of the curves, because elliptic curves in some sense will be the only curves for which you always have granted that you have a rational point, a solution. In the sense that genus zero curves, you can have that either they have no solutions or infinitely many. For higher genus, you have, for example, all the Faulting's results that they tell you that it's very rare to have rational points. And in fact, if you have them, they are finitely many, usually. Elliptic curves, in some sense, are the best thing because they give you all the wide spectrum of the number of solutions.
This one was a conjecture, right? He proved the last.
Yes, the last one was a conjecture. It proved in the 80s, I think, by Faulting's.
Okay, but so it's not the proof is not recent one, but it's
The elliptic curves case is the one that is conjectural.
Okay, but that's different. Yes, to understand how many rational points, yes, it's conjectural for elliptic curves.
still a conjecture.
Yes, you have some subcases where this is solved, but in general, it's still conjectural. Yeah. Okay. So elliptic curves always have this infinity point, which will be important. And the last thing that I wanted to say is that, okay, until now, I was just implicitly considering elliptic curves to be solved over the real numbers. But now we know from algebraic geometry that when I study the equation defining a curve, I also have to consider which field are the solutions from. And for example, I take again this example of elliptic curve, and I want to give you three fields over which the elliptic curve will assume a different face. Okay, again, if I assume my solution to be two coordinate points with real coordinates, I have exactly the graph that I drawn here. But what if I take now the complex solutions? Again, I'm actually taking the solutions in the projective plane to be more precise. What I obtain, okay, first of all, let us remind that when I talk about a curve over the complex numbers, we can see them as surfaces over the real numbers because of the relation between R and C. So a curve is actually a two-dimensional surface. And the nice thing about elliptic curves is that as complex manifolds, elliptic curves are tori. And actually, you can do the vice versa in the sense that if you take any complex torus with a complex structure, you can always show that it is biolomorphic to an elliptic curve. You can always show that it is defined by an equation like this. And then, okay, these are typical analytical fields. What if I go, for example, over a finite field? I take the field F3, which is Z over 3Z, the field with three elements. And okay, now the nice thing is that I only have a finite number of points because even the plane with these coordinates is finite. You have at most 9 points. And in fact, here the curve, the elliptic curve, is given only by 3 points. The points with coordinate y equal to 0 and coordinate x equal to 0, 1, 2. And so in this case, the elliptic curve is just these 3 points. Welcome to the field of arithmetic geometry, where curves do not seem like a normal curve. So you see, when I actually talk about an elliptic curve, I also need to specify over which field I'm working. Also because, okay, I do not have time, unfortunately, for this, but the fact is that whenever you have a field of characteristic equal to 2 or 3, meaning a field where the multiplication by 2 or the multiplication by 3 actually makes everything equal to 0, then you also have to be careful about the definition of the elliptic curve, because you need not just a thing like that, y squared equal to a cubic polynomial, but you need also some additional terms in y to give the most general definition of elliptic curve. Whenever instead you have a field, for example, of characteristic 0, like R or C, then you can always reduce actually to a thing like this. So in general, when I take a field which is not a characteristic 2 or 3, I can always assume that the equation of my elliptic curve is given by a cubic polynomial of this form. Okay, do you have any question about this at the moment?
No, can you just repeat what you said about having finite characteristic and different shape for the equation?
Okay.
So if you have finite characteristic, positive characteristic,
yes, if I have a
only 2 and 3.
characteristic, for example, which is 2 and 3, so assume that the field over which I'm working has characteristic 2 or 3, then actually the definition of elliptic curve, the equation that I have to use is something like this. It's y squared plus a1xy plus a2y equal a cubic polynomial in x.
Right.
X plus a6. So this is actually the most general definition of elliptic curve. The one that in some sense is the true equation of an elliptic curve. The thing is that in fields which have a characteristic different from this, what you can do, you can complete the square here in y, so that you only have y squared here with a change of variables. And then you can complete, you can also, how can I say, complete the cube, so that you can remove the term with x squared. If you are in a field like this, you cannot do this algebraic operation because you cannot divide by 2 or 3. Okay, other questions? Okay, so this was an excursus about the subtle things regarding the definition of an elliptic curve. Now I want to explain why these objects are so important from a geometric point of view. I actually have to say from an algebraic geometric point of view. So second part, geometrical properties of these. So in fact, yes, elliptic curves are, I would say, worshipped by the mathematical community for several reasons, and I want to start with the geometric reasons. The first one, as I already mentioned before during an answer to a question, is that in fact they are curves of genus 1. We can think informally at the definition of genus as the number of holes that the curve has when I think about the curve as a two-dimensional surface. And yes, as I told you, the elliptic curve, when I see them as complex curves, they are complex tori. And I think that in fact you can show that all curves of genus 1 are elliptic curves. Yes, it is also true the vice versa. And so you see that in some sense they are the...
In 10 minutes, we have to make a break.
Okay. Yes, in some sense, this is a typical example of why elliptic curves are the most simple, non-trivial object in algebraic geometry. Because, okay, if you take the curve with genus 0, then you can always reduce to the sphere. And this is one of the reasons why elliptic curves are not ellipses, because ellipses, in the end, are surfaces of genus 0. And these are boring, in some sense, too easy to study. Then you have elliptic curves, which are the complex tori. Simple, but not simple enough to be boring. You can do a lot of stuff here. And then you have curves with higher genus. Like, for example, there are the so-called hyperelliptic curves, but you have also other curves, which, okay, they are interesting, but they are, in some sense, more difficult to study because you do not have such remarkable properties as for the elliptic curves. So you see that elliptic curves stand in the middle between easy things and interesting things. And a similar behavior happens if, now let's do it here. I consider another aspect, which is the algebraic aspect, in the sense that elliptic curves are nice because their geometric structure gives an interesting algebraic structure, which arises exactly from the geometric features of the elliptic curve. What do I mean by this? I will explain this by referring to the classical drawing of an elliptic curve, just to explain the group law here. The idea is that elliptic curves have a nice enough equation to define a law of an abelian group, which arises exactly from geometric features. For example, suppose that you want to do the sum of 2 points on the curve, A and B. So I want to find a third point, which I call A plus B. The first step is to take the line between the 2 points A and B, and now I find it here. I find, okay, this is B, this is C. You can always find a third intersection point here when you draw this line, because you have a cubic equation. Just a remark, when I'm doing this, actually I'm doing it in the projective in order to have all the solutions. But you can always find a third point C. Now, this C, it's not this one. It's just an intermediate point that I need for my operation. Because the second thing now is to take the line between C and the infinity point of the elliptic curve. This is where the infinity point is really needed, because it is really helpful for the group law, and in fact, it will be the neutral element of this group law. So I draw the line between C and the infinity point, that here I can draw as a vertical line. Again, this line gives a third point of intersection with the curve. And this intersection point will be exactly the point that I was looking for, the sum of these 2 points. Now, this is an intuitive explanation of what is happening, in the sense that when I'm really doing the group law here, when I say draw the line, means that I have to find the equation of the lines joining the points. I have to do the system of this equation with the equation of the elliptic curve, find the coordinates, and so on. But if I do this, then what happens is that my elliptic curve with this operation to my elliptic curve, I call it E. I chose the infinity point. I take this operation, then you can prove that the points of the elliptic curve with this element, base point, and this sum, this is a commutative group. And this is the first algebraic reason for why elliptic curves are so important, because they have this abelian structure of group, which arises from, in some sense, very natural geometric features of the curve, in the sense that this is not an artificial procedure. It's something that really is connected with the nature of the curve. And in fact, okay, I have to mention also that here, when I take the points, if I assume that the 2 points I have chosen have k coordinates in a field k, also their sum will have their sum too will have k coordinates, meaning that when I take just the points with k coordinates, I actually obtain a subgroup of this group. And the group of k coordinates, when k is a chosen field, is a very important group, especially for arithmetic applications. I just want to mention also that when you have to prove that this is indeed a group law, you know that you have to verify the several axioms of groups. I think this is the only example in my knowledge where the difficult part of the proof is the associativity law. Because it is very, for example, it is very immediate to verify that this is commutative, and also that the infinity point is the neutral element. The really boring and difficult part that you really takes several pages also of Silverman's book is to verify that this is associative.
Here, when you say line, it's a linear equation.
Yes.
And can you see the commutativity using geometrically? Can you see how y is commutative?
Yes, but because the commutativity is just, you can see already here from the definition, just choosing 2 points, the line is the same.
So it's really the line.
Exactly. And also you can say, because maybe you can think also, what does it mean to sum a point with itself? Just take the tangent in this case.
I think that is a good moment for a short break.
Okay, as you wish.
What about you?
Sì, termina